Hi. First of all, thank you for the invite. I'm happy to be here and to share the perspective I and a bunch of other people have been working on. If you have to take away one slide or one idea from this, it's that, this is the current state of machine learning. We stir a bunch of linear algebra and GPT-4 comes out. We have some idea about how to stir the pile, but we don't really know what's going on. The hope is to start knowing what's going on through the perspective of this language called category theory. So this is what I'm going to be talking about today, the fundamental components of deep learning. First of all, this is I'm actually holding my Viva tomorrow on the same topic. I've been writing a PhD thesis on this. So you're actually getting the unfiltered first-hand view of the presentation of the idea of what my thesis will be about, or is about, better said. So I have this first empty slide here called deep learning, where I'm giving you motivations about why deep learning is interesting to study. Given that this is a machine learning seminar, I might just skip this. We have all seen Stable Diffusion or GPT-4, or all the transformer architectures, all the interesting stuff that's happening. So it's really important and it's changing the world in significant ways. But what's important to know is that this field is a new field when we think about it in the grand scheme of things. And scientific fields, when they often start in an ad hoc manner, meaning that throughout the years, throughout centuries, the practitioners understand them in a very different way than the original people who have studied this. So the classic examples are, in taxonomy, people have been grouping plants and animals for thousands of years, but once we have understood the concept of evolution, our understanding of what they were doing is changed drastically, and our theories are very different, and we have this inductive bias that guides us about thinking about this. When it comes to programming, right, it started with tinkering with transistors and these vacuum tubes, but if you look at theories of object-oriented programming or say functional programming, it's very much abstracted from that. And when it comes to chemistry, this is a particular relevant example. People have been tinkering with low-level chemical reactions, but that changed drastically again with the discovery of the atom and all the quantum things, so to say. And actually, chemistry, when it started as, in many ways, it started as alchemy. And this is quite an interesting case study, because alchemy, despite its mythical reputation, alchemy worked. Alchemists were responsible for many practical advancements in the field. These includes, the development of metallurgy, modern glassmaking processes, lab equipment, and they conducted systematic studies of chemical substances and their transformations. They documented many new and, at the time, unexplained phenomena, such as, fermentation, sublimation. They sort of understood that some reactions absorb heat while others release it, but they didn't know about what we call them today as endothermic and exothermic reactions. They had no understanding of fundamental principles, and their theories were ad hoc and largely based on heuristics. And interestingly, they also had grandiose motivations. So there's all these talks about elixir of life and and many different things that guided. They tried to find a cure to all diseases. And in many ways, deep learning is today in this alchemy stage. So first of all, deep learning works. We have countless things that it changed on our phones, on our systems that it does. It's been responsible for many of these practical advancements. And we are, in many ways, just like alchemists, documenting new and unexplained phenomena. So some of them are here, like double descent, grokking, lottery ticket hypothesis, scaling laws, in-context learning, and many others. But just like I am claiming here that just like alchemists, we have no understanding of fundamental principles. we have theories, and we have, not to say we don't have specific theories, but many of them are largely based on heuristics. And despite us understanding individual components well enough mathematically, their compositions and combinations are generally not well understood. And as an interesting thing, there's also grandiose motivations in the deep learning field of creating AGI and artificial superintelligence. Now, I want to add a caveat here, is that what happened to alchemy? Well, alchemy turned into chemistry. Today, we can actually cure many diseases alchemists were trying to cure. But our understanding of what we are doing is based on completely different principles. And the question is, what is happening to deep learning? What can we take from this? Like, just very short introduction. Well, first of all, deep learning community is aware of sort of the lack of mathematical foundations. The analogy with alchemy is actually originates from a NeurIPS desktop's time award talk from Ali Rahimi in 2016, which I sincerely recommend to watch. It's a fascinating talk about the state of the art of current deep learning. And deep learning researchers organize various workshops on compositionality of deep learning components. I can give references to this later. I actually haven't put many of them through the talks. I'm more than happy to answer any questions if people have them about particular points that I refer to. And there have been calls in the deep learning community about creating a deep learning Langlands or Erlangen program. So these were both far-reaching mathematical programs aimed at unifying separate areas of mathematics. But there doesn't seem to be a general consensus on how exactly to reach this goal. So in parallel, category theory has been happening as a field actually since the 70s, but in the last 5 or maybe 10 years, it has started to gain traction in the form of applied category. It's a field, it's a language that originated in abstract mathematics, and it's based upon the idea of compositionality. It is extremely hard to explain and to give a sense of how you can use it and what it does. It takes a long time to sort of soak this idea in, but I'll just give some very high level clues and ideas, and hopefully throughout the talk maybe we'll get a sense of what it is and how we can use it. People have been calling it the 21st century mathematics, and I really think of it as a good way to organize thought. It's I think about it like refactoring your code. If you have a big code base and you want to extract out pieces so that they're used only once and make it abide by many standards in programming that make our code more consistent and clean, the more we abide by this principle, it's going to seem like we were abiding by the laws of category theory. And a quote I particularly like was from Tom Leinster from his book Basic Category Theory, where he says, category theory takes a bird's eye view of mathematics. From high in the sky, details become invisible, but we can spot patterns that were impossible to detect from ground level. So in a way, you can study all these subfields of category theory, geometry, algebra, many different aspects in a unified way from high above, let's say. And as we're seeing recently, this can be done to many different scientific fields. What category theory has been doing to science is a different topic, but an interesting one nonetheless. So we're going to get a sense of what category theory is in more detail later. But I want to sort of explain now that what is the intersection of category theory and machine learning. I am not the first one to be talking about this or to be doing this. And as a matter of fact, there's many researchers and a steady growth of papers throughout time. As you can see, it's I'm counting the 20 papers here. I think there's probably, imagining I missed half of them, there's 150, which is still a relatively low number, but nonetheless, the growth has been happening. A very slow, but a steady growth. And one question sorry. So I came at this point now while telling you about category theory and what it is, and I promise to give you a sense of how it's going to work. But I want to address one potential thing, which is what people might ask already. Well, okay, what did we learn from CT? What are the new insights? And a good way to understand the positioning of a field with respect to how much it's been formalized by category theory is with this very good quote from Baez and Fong. I didn't put the name of the paper, but it's a compositional approach to passive linear circuits. And they say the following thing. While diagrams of networks have been independently introduced in many disciplines, we do not expect formalizing these diagrams to immediately help the practitioners of these disciplines. At first, the flow of information will mainly go in the other direction by translating these ideas from these disciplines into the language of modern mathematics. We can provide mathematicians with food for thought and interesting new problems to solve. We hope that in the long run, mathematicians can return the favor by bringing new insights to the table. So what this tells us effectively is that, and what my talk is going to be about today, is taking things that you know about. If you're doing deep learning or machine learning, taking things you already know about and saying them in a very weird way. That's effectively it. At some point, as we translate these things, so by the way, once we say these things in this way, this is such a radically alien and different way of thinking, but a very compositional one, meaning it is easy to move across different fields, apply different off-the-shelf tools, and have a systematic sort of not ad hoc way of understanding what is happening. And deep learning currently is mostly in this first stage of saying existing things that people already know about in this language. And it takes a long time to translate these results because it's a very strict language. But as time is now passing, we are slowly getting ideas and new results that we can translate back into deep learning and say, well, here's a new thing that you can do. And this is a classification of type 1 versus type 2 field of ACT, of applied category theory. It's a rough rule of thumb which tells you a field is type 1 if we're merely translating things one way and not saying anything new yet. And type 2 means we have gone the full circle and contributed something new. Because it's such a lengthy process, deep learning is currently in between type 1 and type 2. And hopefully this talk and further research that will happen will push us and allow us to say interesting things. So that's a very long interlude, but I believe it's good to give context about what is happening, because this is a long-term research project, and I don't have I don't expect you to learn from this talk what category theory is, or to get a good sense of how exactly it works. It's a really hard thing. I think for me it took so long to get to the basics. Well, maybe you're faster, maybe you'll catch this, but it's I just want to set the standards about set expectations for how this thing is going to work. So the goal in today's talk is to give you a sense of to report to you the progress made on providing a categorical framework for deep learning and giving a sense of what it can do. What it can do back and tell us new about deep learning. So here you can see a particularly curious graphic of something, and the idea is that there is a graphical and formal way to understand neural networks, and this is how we're going to be thinking about them here. as this very weirdly shaped thing. And I'm going to explain what all the inputs and outputs mean, but there is a very systematic formal way of assigning neural network semantics to parts of this diagram. And actually, you can think of it as animated. You think of it as, I'm going to tell you right now, so P represents parameters, X represents inputs of your neural network. And you can think of, given a parameter and an input, you can produce an output Y, which is, say, your classification of the neural network, or perhaps an input to the next layer. Once you do that, you also save some internal state, which is the information that you use to compute the backwards pass. So this is blue here. That you use to compute the backwards pass once you receive the gradient. And we're going to see now that once the gradient arrives here in form of y prime, we can use that saved in intermediate state, which is often just the information about the point we are taking the derivative on, and the incoming gradient to compute a new parameter update. That's a very rough story, but we're going to see what this means formally throughout the talk. Well, I've gave it away already. I have a slide here that tells you, well, it's actually 2 slides, what supervised learning is. So our task is to find a function from X to Y. So we know the type, but not the implementation. And we want it to best fit some data set of input-output pairs. So this is the classic definition of a supervised learning problem, where, of course, what best means needs to be specified. The way it looks in practice is you might have an input X, which is, say, an image of a cat, and you might have a label, which is usually a probability distribution. In this case, it's a Dirac at 1 at cat. Basically, it's 100% cat, and it's a 0% of a dog and 0% of horse. The way the learning works is that you take this input and pass it through a neural network. Computation being done in a neural network is being done in a series of layers. So this image, first of all, is encoded as an array of, or as a sequence of pixel values, and we pass that into the neural network. Of course, the architecture can vary wildly, but the neural network step by step computes, given some input weights, what the output to the next layer is, and that next layer uses that as an input together with the information of the neural network weights, which are here encoded by the thickness of the wires. Once we get to the last layer, we encode it in such a way that we get a prediction out. So we might get 40% cat, 50% dog, and so on. And in our learning process, we want to compare this guess with the actual true guess and get a number out, quantifying how far away we are from this, from the true answer. And now that we do this, we embark on this process called backpropagation, where so if you look at the loss function, well, we know the way we can jiggle the output Y to get a smaller distance to this Y. So if we know how to do that, we know in which direction we have to jiggle it. Well, then we can say, okay, which way do we have to jiggle the weights so that we get that desired Y? And then once we get that answer for each of the weights, we can say, well, which way to jiggle all of these weights? And once we do that, we can actually update the neural network. And we have done one step of optimizing. So here we see, so this is the classic story of supervised learning. And the reason why I'm studying this is, I said, I'm going to study basics here. But the way you see, there's lots of different components happening here in this system that are not clearly disentangled. So first of all, if you think about processes, right, we're composing some processes together here, but some of them are parameterized. Neural network weights have these extra inputs that are the weights. And the loss function also has two inputs. You know, are the labels sort of like weights of the loss function? It's well, in this diagram it seems to be suggested like this, but a lot of this intuition isn't really formally specified. It's in the diagram. I have told you about it, but you might miss it if you didn't think about it. And of course, I didn't even draw these neural networks because all these wires in effect are doubled. We have a forward pass and a backward pass. So when we talk about neural networks and the way we train them, there's many different parts interacting together. Thinking of neural networks simply as processes, there's two different things we have. They're both parameterized processes. They have weights coming in, and they're both bidirectional processes, meaning information flows forward in the forward pass, and some notion of change or update flows backwards. So the question is, how can we formally specify this? How can we disentangle these components in a specific way and put them all together as we wish? So this is the idea of the talk today, specifically, is to disentangle these components of the black box of neural networks, to talk about parametricity and bidirectionality as separate concepts. What is interesting in doing this is that once we extract and say in the abstract about what it is that we really require when we say talk about neural networks being parameterized by weights, well, you know, we don't for neural networks specifically, we need things to be smooth, but to talk about the essence of the notion of maps having parameters, we don't need, say, the notions of Jacobians or smooth spaces or something like this. So the notion of having parameters as input is more general. And of course, when we talk about bidirectionality, what we propagate backwards is also up for us to decide. And if we extract the notion of bidirectionality separately on its own and study it on its own, it turns out we end up starts looking a lot like many other different fields in not just machine learning, but in areas of science and math. So for instance, the same construction we're going to be using today to study backprop can be used in game theory to propagate back payoffs for economic agents that are optimizing some particular goal. You know, it will also turn out that you can do, when you do reinforcement learning and specifically value iteration, you can, the same way we backpropagate gradients here, there is an analogy in reinforcement learning about what is being backpropagated in value iteration. Of course, you know, when it comes to differentiation, this is a well-studied area of math in terms of differential geometry, and we're going to see a lot of concepts are literally the same in as we're using them here and in this field. And of course, there's the fields of dynamical systems and control theory and many others that I hope to make some formal connections to. But of course, there's a lot of work and about half an hour left. So I'm going to start, and we're going to see how far we get. And please feel free to ask questions if things are not clear. As I said, I might, if you are a machine learning practitioner and you're doing neural networks every day, I might not tell you anything new, quote unquote new, but I will hopefully give you a new perspective. Right. Okay, so let me take a sip of water. So I've talked a lot about category theory, and I mentioned that I will give you a sense of what category is, what categories really are, and what is the field specifically about. So the field of category theory studies these concepts called categories, and the idea is you think of them as a network of relationships. And so, for instance, one network of relationships might be, you know, you have some. I'll just delete this and try everything again. you might have some objects you're studying. I'm just going to call them A and B, but these could be anything you want as long as some particular rules are satisfied. And you have some ways of relating them. I'm drawing this way of relating them as an arrow, but you know, that's the usual way it's drawn. And it's effectively this. You might think this is very simple, but that's effectively what a category is. We have some objects and some ways of relating them, and the power comes from this being at this level of generality, where it can be, your objects can be numbers, sets, vector spaces, groups. Your ways of relating them, as we call them morphisms, can be also pretty much anything you want. Now, of course, if I just tell you, oh, it's a bunch of points and arrows, well, if my theory explains everything, then it's not a good theory. We need some rules and some laws. So in category theory, you have these laws where it tells you, well, for every point you need to have a distinguished identity arrow that does nothing. So if you have sets and functions, your identity will be just the identity function. And that needs to hold for every point, for every object here. And for any two maps, F and G, so if you can go, from B to C and from C to, well, again, B, you need to have a way of composing them. So you need to have an arrow that is G after F. And with these few rules, you can actually rule out many pathological examples that you don't want to have, but actually include a lot of things you really want to have. So it's very abstract, but a precisely specified concept. And so the definition here, as I've said, you have a bunch of objects and a bunch of morphisms between them. And very importantly, that you have a way of composing them. If you have a map from A to B and B to C, you have a map from A to C. You have a way of doing nothing, which is very important. And you have these laws which tell you, well, if you have any map from A to B and you do F and then you do nothing, well, that's the same as F. Or also, if you do nothing and then you do F, that's the same as F. And you also have the rule that, if you have three maps that you can compose, it doesn't matter which order you compose them in. And that's it. So that's it. This is the definition of a category. And you can notice a similarity with the concept of a graph. So a graph is like exactly a category without these rules. Basically, you have a set of edges, a set of nodes, and a set of edges. So categories come in many shapes and forms. So there's the category whose objects are sets and morphisms are functions. There's the category rel whose objects are sets and morphisms are relations. There's a category vect whose objects are vector spaces and maps are linear transformations. There's a category. Oops. Can you still hear me? I think everything should work.
Yes.
I think great. There's a category of real numbers, R, whose objects are numbers, and a map from 2 to 3 exists. A morphism from 2 to 3 exists if there is an order relation between them, and so on. There's the category of groups and so on. And the idea is that we often use categories to build other categories. We describe abstract properties thereof. And we can do so many things. And the question is, can we describe any of the aforementioned properties of neural networks in this very, very abstract way? So if you look at the basic neural network layer, so we usually write it like this. So it's a function that takes a k-dimensional vector and outputs a k-prime dimensional vector. So it takes an x. And the way we usually think about it is, well, we take this vector and multiply it by a matrix and then apply some nonlinear activation function. So, you might already think, well, okay, this looks sort of like the category vect of vector spaces. We have objects, some vector spaces and maps. Well, it's not a linear transformation, right? And we also have this data of the weight matrix. So, and this is a data of, that is that each layer chooses, basically. Each layer has its own data of a weight matrix. So there's a way of modeling this in category theory, and I'm just going to tell you, and I'm happy to take questions. As I said, this talk is going to be very high level, and there's not enough time to go into all the details. So I will unfortunately have to skip over some of the math, but hopefully this gives you a sense of how things work. So the idea is as follows. The story of neural network weights that had inputs and weights encoded implicitly by the thickness of the wires, we can turn that into a formal process, so to speak, where we have inputs coming from the left, outputs coming from the right. So if I ignore the top part, if I ignore the top part and just look at this bit, this is just a standard process. But here we're going to have parameters that are going to control also what the output is. And this is the main idea. We want to describe processes of this shape in a very general way that doesn't assume anything about the kinds of functions we're differentiating through or things like that. And the idea is that we fix something called a monoidal category, which is a category where we can compose processes not just in sequence, but in parallel. And then we can form a kind of a category which has this extra sort of inputs. Formally, mathematically, what is written here is that the set of morphisms from A to B, if you remember our story with objects and morphisms, we're saying that each morphism from A to B in this category that we're calling para C consists of a choice of a P, which is the parameter space, and the function f, which goes from a morphism f, which goes from P times A into B. And we might have another morphism here, which has Q, and then it consists of a morphism Q times A to B, and so on. And importantly, when we want to compose these morphisms, we get an automatic way of doing so. So we have P and F here, and let's say R and H here. We get an automatic way of doing so. So when we want to compose these things, there is a nice graphical way of thinking about this. So we can take our map F with the parameter P, take our map G with the parameter Q, and simply put them side by side, and get a new map that is now written in blue, in this blue here, whose parameter space is P times Q. So maybe I can just make it, I'll write times like this to make it more clear. This is the Cartesian product of sets. So interestingly, this models how actually neural network composition works. I've never seen it written like this when I read about neural network literature. So we know that when we compose neural networks in sequence, when we compose neural networks in sequence, their weights get composed in parallel, so to speak. We have, once I compose two of them, I still have two inputs for weights, and the more neural networks we compose, the bigger the weight space is, the more parameters it has. So what we're doing here, again, if you're doing deep learning, you might instinctively know this. What we're trying to say here is translate this to a formal language where we can systematically verify and check these claims, and B, where we can, where we also have a formal graphical language for thinking about this. And once we have done this, we are no longer restricted to thinking about the reason why I wrote here this times, because I don't necessarily need to talk about a pair of two things. Maybe I want to talk about more abstract notions of putting things side by side. This could be plus, where I say I have either a P or a Q. And there's many other notions of joining parameters together that become useful later. So this tells us how to describe parameters. Oh yeah, and what I've been using here, let me see if I can move this somewhere up. What I've been using here is a formal graphical language of string diagrams to talk about these things, which is quite a useful way, I reckon, to talk about neural networks. Because if I think about a map P times A into B, I have to draw it like this, and I have to take care of the parameter. And if I draw it just as as two wires, as P coming from the left side, I am ignoring the fact that the P is the data of a morphism. It's the data of the neural network. It's the private knowledge inside the network that is not available to the outside world. So the idea is to really draw these things like this. And then this enables us to talk about notions of reparametrization, where we can re-index the parameters inside the network and perhaps do weight tying and similar things in a relatively elegant way. So given our example from before of this neural network, we could translate this into our language of parametric maps. So here we see that we have this neural network has 4 inputs. B here stands for the bias layer. So here we have 4 inputs, and correspondingly, our morphism has the domain R to the 4. Now, the output of this thing is 2-dimensional. Correspondingly, the output is R to 2. Now, we have parameters here which are invisible, but we are making them explicit in the story on the right. So we can see what it says here, and basically this enumerates the weights, right? So we have 4 times 2 weights, 4 times 2, because we do all the combinations of inputs and outputs. So this is 4 times 2, but we also have the bias layer, which is this node that always has 1 inputted, and this gives us, it translates each of these up and down, each of these nodes. So we have 2 bias nodes. And the story for the second layer follows analogous. So we can translate the language of neural networks with these diagrams into these things, which is going to end up quite useful later. One way, actually, I can tell you right now how it's useful is that you can do weight tying really naturally. So I assume for a second that we just had one weight on both of these, or maybe that both of these were R to the 2. Well, you can, if you think about how to do weight tying, how to graphically denote it in this image, well, you can't. You sort of have to say, well, okay, this node is going to be the same weight as this node. Maybe you can color it in, and this node is going to be the same as this one. But it's a bit fiddly. In our language, we can just compose a morphism on the vertical direction and say, well, actually, we have an output R2, and we simply copy this parameter into both neural networks. So they operate as receiving some weight, but we behind the scenes know that it was caused by the copy map and the same set of weights. Right, so just to get a sense, I see that it's 20 minutes until the full hour. When should I aim to finish with regards to questions and everything?
Yeah, you can finish at 11.
Okay, sounds good. Right, so that tells us about parametric maps, and it gives us a way of modeling them without resorting to some relatively ad hoc diagrams. We can model them like this, and then we can translate this story to other settings. We can model in game theory, people model these things where we have strategies here and some inputs of economic agents, and they compute the outputs and so on in the same way. So this model is the parametric aspect, but now we have the notion of bidirectionality. So this is a big story as well, and I'm going to give only a cursory introduction to this. The idea is that this is also can be modeled as a morphism in some category. now our morphisms are going to be bidirectional. So in some sense, we're going to have objects which have pairs of objects on the domain and pairs of objects on the codomain, representing the fact that we have an input on the forward pass and a gradient received on the backward pass. And here we have an output on the forward pass and a gradient received from the other end on the forward pass. And really, what we're writing down is what you might already know as being backprop. Well, we have what is a morphism here of this type, and here we see. So here is, by the way, before I go, I'll just tell you the rough flow of information, which you can see. We get an input here, we save the intermediate state. Once we receive the gradient, we use this intermediate state. And formally, what I'm writing down here in the definition of this optic is really just this. I say an optic, a morphism in this category, consists of three things. A, the type of the intermediate state M, which is the residual, which is the data you choose to save for the backward pass. And depending, for instance, on efficiency reasons, you might save different things. This becomes important in automatic differentiation. And we have a forward map, which takes an input, produces an output and this intermediate state, and a backward map, which uses this intermediate state and a gradient to produce an X prime. So I'm really just writing down the high level what this does. We can see how this will model backprop and so on. So optics, we call these things optics, and they can be composed in a very straightforward way by just plugging them again. As before. Oh, the animation broke a little bit here. Let's see. Okay, now it works. So we can just compose them like this and get a new optic that has a forward part in blue on top and the backward part in blue in bottom, and correspondingly where we save M tensor n in the mean in this space in between. As I briefly mentioned, these things are called optics in the literature. They also go by the name of lenses, and this originates basically in functional programming, where these are useful data combinators for accessing and storing information. So a lot of these things actually transfer directly to the world of functional programming. And I'm just using this terminology, but optics here has no connection to actual light or diffraction of all of these things. I apologize for this terminology, which might be quite confusing. But basically, we call them optics and lenses. There are some slight nuances that are important to operational aspects about when you actually implement these things in practice. So we can now compose these processes together. We can compose things that are parametric and things that are bidirectional, and get a general story of systems that take an input X, take some internal state, produce an output, and then using the received feedback from the outside world, they can use that to A, update themselves, and B, propagate some useful information to previous composites in this system. So in the story of deep learning, the backwards pass is done by gradients, where I'm really using here the terminology. I compute some y, which is a function of these two outputs, and then what I receive here is the partial derivative of the loss with respect to that output y. And what backprop does is compute the partial derivative of L with respect to X and the partial derivative of L with respect to the weights. So that's the rough idea here. So how is this useful? What does this allow us to do? And I want to say that this is incredibly flexible. We are still doing research, and I would still call us in the infancy stage but we are slowly being able to describe many architectures that are prevalent in today's machine learning world, and being able to say them, describe them formally, draw them, and say meaningful things that translate, not just that don't just stay in machine learning, but are we can translate into the fields of game theory and so on. So, for instance, I think there's been some graphical glitch here. Okay, I don't think I'm going to be. Yeah. There's the unfortunate behavior of this app. When you write text over an animation, it jumbles them together, so you cannot delete one without the other. So I'll just ignore the animation in the background for now. I hope it's clear. But it's basically incredibly flexible. It doesn't make any assumptions about the architecture. Thus, you can model various things such as recurrent neural networks. So here we have a sequence of inputs. We have a sequence of outputs. And each output in this sequence depends on all these things that come before. So it depends on all these inputs and all the hidden states of the hidden layers. And it basically models a recurrent neural network, where importantly, we can see that there is some weight tying going on. Here, the dot means copy, by the way. So here we see that at each point in time, we're using the same parameter for each cell of the recurrent neural network in the same layer. For the different layer, we use a different parameter, but again, same throughout all the cells in that layer. And the same goes for the third layer here. So this is quite a neat graphical description of what's actually happening. We see what information is actually flowing, what is tied. It is not the case that this parameter is used here, because that's the second layer. It's only used in the first layer, but inside that layer, it's being copied. We can also model generative adversarial networks. So this is a very, it turns out you can describe it in this very high level way, where you model a generative adversarial network as a composite of a few systems. This composite consumes either an image, a real image, or a random vector. And then if it consumed a real image, it just passes it on to the discriminator, which then says whether that image was real or fake. But if it gets a random vector, it uses the generator to create another real image X. And this thing here erases the information about where the image came from. It's an important thing that makes GANs work. Here I'm using plus and minus as a very high level signs of telling you here I'm doing gradient ascent and here I'm doing gradient descent. You can actually also flip some of these things around if you're careful, but that's the rough idea. We can model convolutional neural networks, recursive neural networks, very rough forms of graph neural networks as well. So there is a lot of research on geometric deep learning happening in many ways in parallel, but being tied together by category theory that we're hoping to merge with. So, and all of these are just parametric lenses. So at this point, I have this slide called future work, but I thought I would give a remark about what it is that we have done so far, which was a very very fast way of tracing out a path through this research and throwing at you a lot of concepts. So what we've done is establish maybe where deep learning currently is. We have a lot of ad hoc approaches and not a formal way of understanding them, not a unified theory that can capture things such as backprop. parameters of the neural network, updates, talk about the whole step of supervised learning at once, and all of these things. And the premise and the claim of my thesis and this very fast talk is that category theory is a good tool for helping us do this. As it has only recently started being applied to deep learning, apologies, as only recently it has started to be applied to deep learning, the developments are relatively reserved in the sense that we're only able to, at the moment, we are only able to say sort of the things that you might already know about. We are recasting them through a different lens, through a different perspective, but so far we are being still quite limited in being able to say something new. Partially the reason for this is just the incredible pace of the development of deep learning. A good way to see this is to compare this with game theory. So in the group I'm working with, which is the mathematically structured group at the University of Strathclyde in Glasgow, we use category theory to study not just machine learning, but reinforcement learning, game theory, in general, the concept of cybernetics, where we study these things without a reference to the specific kind of an implementation. And the progress made in game theory has been quite impressive, and a lot of new things have been said already. This is partially because the field of game theory is comparatively small to the state of the art of deep learning, and B, because the field of game theory doesn't have the good practical software development mindset compared to, say, the insane DevOps that is happening at machine learning in industry. So at the moment, it's interesting to see that in game theory, it's quite easy to make software and quite easy to make new progress using this compositional way, which the industry hasn't caught on because it's much slower. But in deep learning, we are very far from sort of well, it's quite hard to say whether we're very far, but certainly the progress has been outpaced by a lot of the new research. And at the moment, we're catching up and slowly hoping to fill in the blanks. And we're getting a lot of cohesive theory at the moment that is being translated across the field. And that's extremely exciting to me. And I'm hoping we get interesting things out that we can say with this language. Category theory is an incredibly deep subject, which I've only had a very short time to give you a sense of. But I invite you to well, I was going to have references here, but I didn't have too much time to put them in. But I'm more than happy to answer questions after this, or to pinpoint references, or to get your emails. I have a lot of things online with references. But yeah, future work on this front really entails thinking about a general theory of architectures. Can we come up with new architectures? Can we come up with higher order architectures, things with produced architectures? Can we make establish connections to meta learning and iteration, and connections with game theory, probabilistic programming, which I've completely missed in this talk, and many other things. So we have done some work, and we're hoping to do much more. And this is where I will end. Thank you.